some specific methods in differentiation. Like we learned the properties last time of constant multiplied by a function, or the distributive type of properties. So like that, we'll understand some more properties as well as some more formulae. Okay, and some of these formulae we are not going to look at the derivation of how the formula comes from the fundamental method, but at the same time the derivation is not something too difficult. The reason why we will not learn it here, because we don't really need the derivation in physics. Our purpose is just to be able to apply differentiation to physics problems. But differentiation by what is called first principle, or differentiation by the definition, that limit method, is going to be a big part of your advanced calculus in mathematics in 12th. So like we have derived the formula for differentiation of x cube or x square. So those type of problems can come as questions of your class 12 maths, and you will have to be able to work out the formula from the limit method, like we have done for the x cube one. So that will be very much part of your math syllabus. Okay, but at the same time, if you're curious for the definitions, for the derivations, there's no harm in trying them out yourself, or you can seek out my help again to give you some direction about how you can work out the derivations. It's just that for the purpose of physics over here, we don't need all the derivations. So we will be just looking at the formula in most of the cases. Okay. So anyhow, so just quick recap of the things that we learned about differentiation last time. So we saw that if we have a function y is equal to fx, okay, then the process of differentiation applied to the function, or you can say the operation of differentiation applied to the function, what it gives us is the instantaneous rate of change. Okay. And what we also do is that, because, so for example, we know that if y is equal to, let's say, square root of x, we know that the process of differentiation applied here to the function root x, we know that that gives us 1 by 2 root x. So you can see this thing is itself a function. So dy by dx, the derivative itself comes in the form of a new function, where if we substitute the value of x as something specific, then that gives us the slope of the tangent at that particular point. Okay, so now we understand that once we get this thing, now from this we can say that therefore that the slope of the tangent for the function y is equal to square root x. Okay, so slope of the tangent also means instantaneous rate of change. Okay, at any specific value of x, let's say x equal to a, suppose. So that is equal to, so that slope of the tangent is equal to 1 by 2 root a. Okay, so that is the interpretation of this process of differentiation. Okay, now what we also do is that the short form that we use for differentiation, that operation of differentiation applied to a function fx, is in short sometimes written as f prime x. So you might see this notation in some advanced books or reference books, etc. So the prime symbol just means that it has been differentiated. Okay, so this thing is called the differentiation.
Sir, but dy by dx is already a short form only, right? Where we write limit delta x
d by dx is actually an operator. Okay, na beta?
Okay, sir.
What you are referring to is this, na, that differentiation of this function is given by this limit. No, you are saying it's a short form for this, right?
Yes, sir.
So see what I'm writing on the right hand side now, this is the definition of the operation. If we ask ourselves that technically maths wise, what is the meaning of this operation, that d by dx of fx kya hota hai, then that is this operation. Understood, na?
Achha, okay.
So this is the definition. Okay, whereas this is the symbol. Okay, and this symbol is also sometimes too lengthy to write now, so we just write a short form of it, that f prime x means that it's the differentiation of fx with respect to x. Okay, na? Understood this point?
Yes, yes.
Okay. And it is also sometimes called the derivative of the function. Derivative means the same thing as the differentiation of that function with respect to the independent variable. So derivative of fx. So these are some alternate terms that are used. Okay, so this is just a matter of nomenclature, how we use the terms. Okay, so that is that. Okay, so these are the basic matters that are clear to you. Okay, now we had seen the basic formula last time, that differentiation of x to the power n is nx to the power n minus 1. Okay, so the proof of this also comes from that very simple kind of process only, that the definition of this operation is that it is the solution of this limit delta x tending to n, x plus delta x to the power n minus x to the power n divided by delta x. Okay, but the problem with now proceeding further is that we don't have a direct formula that we know as of now for the opening of this bracket. Okay, so that is where something called binomial theorem comes in. So we will discuss a little bit about binomial. Rather than the whole theorem, we will discuss about binomial approximation method, which is going to be something very useful in physics as a maths tool. Then we'll come back to this derivation. So the binomial approximation method, the basic formula of it is very simple, that if I have the expression 1 plus x to the power n and x is very small compared to 1, then I can approximate this thing as 1 plus nx. Okay. So before we jump to any conclusions about this, that why it is like this and all this, let's just look at some examples. So suppose I have 1 plus 0.01 to the power 2. So what I'm saying is that this should be approximated as 1 plus 2 into 0.01, which is 1.02. So just check the efficiency of this. Okay, just check it out. If you do the full operation, it is going to be 1.01 square. So how much would be 1.01 square?
1.0201.
1. Yeah, so it will be 1.0201. So approximately it is equal to 1.02 only. So this is correct. If we round it off up to second place of decimal, this will be correct, right?
Yes, sir.
Okay, let's check out another example. Suppose we have square root of 1.04. So according to this method, this is, so this should be approximately 1 plus half into 0.04. So this should also be equal to 1.02. I'm just going to use my calculator, okay, to do the exact calculation. By calculator, I will get square root of 1.04. Let's see what we'll get it. So I have 1.04. Okay, and I'm going to do the square root of it now. So hopefully you guys can see this. This is coming from the calculator as 1.0198039, something like this. Okay, so you can see that is approximately equal to 1.02 if I'm approximating up to second place of decimal. So just by showing you some numerical examples, I'm just establishing that yes, this is giving me the correct result. Now there's a logic behind this also, and we'll come to this also. But remember that this approximation can be done only when this condition is satisfied, that x should be very small compared to 1. Okay, so for example, if I apply it for this, let's check it out for something like this, square root of 1 point, let's say 21. Okay, so this might not be so effective. It depends. Okay, so it is 1 plus 0.21 to the power half. So if I apply this approximation method here, now it will not be such a good approximation, because as you can see, 0.21 is not exactly very small compared to 1. This is not necessarily a correct statement, because it's greater than 1/5 of 1. So it's not extremely small, but still let's see what we'll get. So we'll get 1 plus half into 0.21, and that will give us 1.105. And even this is reasonably correct, because you know that square root of 1.21 is actually how much? It is 1.1. So this is reasonably okay. But if you go a little bit further, now you try out 1.69 square root by this method, by the approximation method, you'll see that the approximation is not so valid because 0.69 is even larger than 0.21. So it's not so good. Okay. So we can only apply it when, in general, when x is small compared to 1. The smaller the value of x compared to 1, the better the approximation is going to be. Okay. So if you like, you can just make a note of this method and these two examples first. Okay. Then we will discuss where this comes from. This comes from this comes by the application of binomial theorem. Have you heard binomial theorem?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes.
It's the general expression of a plus b to the power n. No?
Yes, sir.
Okay, so this actually comes from binomial theorem. So we'll discuss a little bit about that also. And then we'll come back to how this can be used to prove that this is equal to, ultimately, with all the steps, this should come out to be nx to the power n minus 1. Okay, so once you have finished writing down this part, you can try one couple of more simple questions based on this. So for example, you want to calculate the value of 1 upon square root of 1.06, and you want to calculate something like, let's say, square root of try out these two calculations using this. Now, the second one that I've given you, the square root of 9.27, you'll have to innovate a little, okay? Because it is not a number slightly greater than or less than 1, okay? You can also try this.
Sir,
Yes,
sir, could you please scroll up a bit because I had a doubt
yes,
in something.
yes, I'll just. Yeah, this part, Vita, you have some doubt?
Yes, sir. In the true, sir, shouldn't it be limit delta x tending to 0, like, but you have written.
Delta x tending to 0, sorry, not delta x tending to n. My mistake. It should be tending to 0.
Okay, sir. Okay.
Yeah, so if you got the answers to these three parts now, just you can start texting it to me. Yes, very good. Abhinav, Mansi, Prithvi. Yes, that is correct, Jairaj. The question that you have asked, x can be a negative quantity also, but its magnitude should be less than 1, very small compared to 1. And similarly, the power n can also be negative. Okay, so let's see how this works out. So this one, 1 upon square root 1.06. I can write that as 1 upon 0.06 to the power half. And even more convenient, I can bring this to the numerator and write it like this. So n can be any integer, any real number basically. So it can be negative or positive, it doesn't matter. So this is now 1 plus 0.06 to the power minus half. So this is of the type 1 plus x to the power n, where x is very small compared to 1. So it fits that category. So we can say it is approximately equal to 1 plus of minus half into 0.06. So this is 1 minus 0.03. So it is 0.97. Okay. And if I actually do the calculation of this using a calculator, see what I will get. I'll get square root of 1.06 as 1.02956, let's say. Okay. So I'll get 1 upon square root of this as, now if I just invert this, so you see I'll get 0.9713. Okay. So this is a good enough approximation. You can see this is approximately equal to 0.97. So it's very effective. So even for doing calculations in physical chemistry, when you come to that later, irritating type of calculations, you can simplify a lot if you know the trick of how to use binomial approximation. Now for the second one, many of you might not have started, so I'll just give you a hint. So what you can do here is that you can see that if you take 9 common inside, okay, it is 9 into 1.03, and the 9 comes very nicely outside this. Okay, so it's just a trick. It's a matter of observation. Okay, it's just a matter of observation that you can do this over here. So it is 3 into 1 plus 0.03 to the power half. Okay. And then on this expression with the power, you can apply binomial approximation. So bit of algebraic manipulation involved, okay, but still you can see yes, so very good, Nidhish, Prithvi. So next, this just becomes, when you approximate this becomes into 1 plus 0.015, and then you can solve this further. So this just becomes 3 plus 0.045. So you can see that we can approximate this as this. Okay. And again, if I use the calculator, let's see what we get. See, it's going to be very accurate what we have done. So rounded off up to second place of decimal, or rather third place of decimal. This is accurate. Pick this up. Now, what is the manipulation we can use here? We can use a manipulation that this is square root of 4 minus 0.18, and that is further equal to square root of 4 into 1 minus 0.045. So that is 2 into 1 minus 0.045 to the power half. So the minus sign makes no difference. You can just treat it like 1 plus x to the power n, where x's value is minus 0.45, whereas n's value is plus half. Yeah, so Nishay, I will include some questions based on these type of calculations in our next worksheet also. Okay, but see, this is again, I'm diverging a bit from our purpose in calculus, but I need the binomial approximation method first to be well understood to come back to calculus. So I have just shown you some general everyday calculation examples of the application of binomial approximation method. Okay, and this will be useful in various places, not just in calculus, but this will be useful for doing everyday numerical problems in physics in further chapters. Physical chemistry, I give you another example where you can come across these type of irritating calculations which can be simplified by using binomial approximation wherever you see the opportunity for it. Okay? So it's something that will become part of your, you can say, your arsenal of maths tools. Okay? So the next approximation step here will become 1 plus of half into minus 0.045. That is 2 into 1 minus 0.0225. Okay. Or actually, when you open the bracket, that 2 just goes out, so it's easier. So 2 minus 0.045. So that you can see will become 1.935955. And once again, you can check later with a calculator that is a reasonably accurate approximation. So these are some examples of the application of binomial approximation method to actual numerical expressions of this type. Okay. Now let's also understand where the binomial approximation comes from. So it comes from binomial theorem. So the binomial theorem statement is that the general expression of a plus b to the power n is a power series of this type, a to the power n plus n into a to the power n minus 1 b plus n into n minus 1 by 2 to the power a to the power n minus 2 b to the power 2 plus n into n minus 1 into n minus 2 divided by 3 into 2 to the power a to the power n minus 3 to b cube plus a series like this that goes on. Okay. So the general expression of the series is that this will be n into n minus 1 into n minus 2 into n minus 3 going up to some term n minus I, let's say, divided by I into I minus 1 into I minus 2 into, like, all the terms still become into 3 into 2. Okay. So this expression, okay, into a to the power n minus I, b to the power I. This is like the, we say this is the ith term. This is the I equal to 0th term, this one. This is the I equal to 1 term. This is the I equal to 2 term. Okay. This is the I equal to 3 term. And like this series goes on. Okay.
So we can use the NCR formula also, right?
We can use the NCR formula. Okay. So basically this term that we've written now, n into n minus 1 into n minus 2. If you're familiar with combinatorics, okay, you can see that is actually given by a formula. It is factorial n, okay, into factorial I into divided by into factorial n minus I, this kind of term. Okay, but if you're not familiar with all this, don't worry about this. Okay, so just as an example, you can see that when I take a plus b to the power 3, the first term should be a cube. The second term becomes 3a square b. The third term becomes 3 into 2, okay, divided by 2. So that just remains 3 only into ab square. The fourth term becomes 3 into 2 into 1 divided by 3 into 2. So that's 1 only into a to the power 0 b cube. And once this reaches here, the last term where b's power becomes n, the series stops. So ultimately this is a cube plus 3a square b plus 3ab square plus b cube. So similarly, if we had a plus b to the power 5, let's say, this would be a to the power 5 plus 5a to the power 4b plus 5 into 4 divided by 2, okay, into a cube b square, okay, plus 5 into 4 into 3 divided by 3 into 2 into a square b cube, okay, plus 5 into 4 into 3 into 2, okay, divided by 4 into 3 into 2 into a b to the power 4, okay, plus 5 into 4 into 3 into 2 into 1 divided by 5 into 4 into 3 into 2, a to the power 0 b to the power 5. So once I've reached b's power is n, the series stops when we have this kind of a term. So this would ultimately become a to the power 5 plus 5a to the power 4b, okay, plus 10a cube b square, okay, plus again you will see this term will become 10 a square b cube, and again you would see this term would become 5 a b to the power 4, and again the last term would have coefficient of 1 and b's power would become 5. Okay. So we don't have to worry about the full application of this as yet. Okay, this you will learn as a separate chapter in maths actually. Binomial theorem and binomial approximation is just one part of it, but I'm just giving you a basic layout of how this formula works, and this I'm just showing you examples where n is a natural number or a whole number. Okay, there can also be cases where n is a fraction or a negative number, and the formula of the series works in a similar way. Okay, but in that case the power series becomes more lengthy. So in this case the number of terms is n plus 1. It has n plus 1 terms in the series. So you can see that this has 4 terms. Okay. This you can see will have 6 terms because the power is 5. But if the power is something like 1 by 2, or 1 by 3 or minus half or minus 6 or something like that, then it becomes an infinite series. Okay. So once again, like if it is something very new for you and you're finding it complicated, you don't need to worry about this at all. Okay. If you're curious about this, you can look up any standard algebra textbook of maths. Okay. You will find the chapter called Binomial Theorem. Okay. So you'll see more details and description about this process. You can always play around with the algebra yourself. For example, you can derive the formula for a plus b to the power 4 using this theorem, okay, using this series, and then you can also separately do it algebraically by just multiplying a plus b cube with a plus b, and just working out the algebra, and you can verify that both converge to the same series. So you can always invent small little maths questions for yourself and just play around with the numbers. Okay. So now coming back to binomial approximation, how that works is, if I have 1 plus x to the power n, so basically I'm looking at this, but I'm taking a's value as 1 and x's value as, b's value as x. So when you expand this series by binomial theorem, the first term is a to the power n, so it just becomes 1. Okay. The second term is n e to the power n minus 1, b to the power 1, so it becomes like this. The third term becomes n into n minus 1 divided by 2 into e to the power n minus 2, b to the power 2, so x square. Okay. Then the third term becomes n into n minus 1 into n minus 2 upon 3 into 2. This coefficient into again e to the power n minus 3, so that will just be 1 into b to the power 3, so it will become like this. Okay. So this kind of series will just continue, okay, with more terms. So let's say the series will continue like this, with the ith term becoming going up to n minus I. Going up to 3 into 2 in the denominator. So this is the coefficient of the ith term, and the power will become x to the power I. So this becomes basically a power series in I. So for example, if I have 1 plus x to the power 4, according to this theorem, it should be 1 plus 4x, okay, plus 4 into 3 divided by 2, so 12 divided by 2, so that's this, okay, plus again this term will also become 6, okay, then we'll have a term 4x to the power 4. Finally, sorry, we'll have so this will become like this. Okay. Similarly, if we have 1 plus x to the power, let's say half, so this will become 1 plus half x plus, now this term will become half into half minus 1 by 2 into x square, plus the next term will become half into half minus 1 into half minus 2 divided by 3 into 2 into x cube, and like this series will continue. The only difference is because now this is a non-natural number. Okay, so this series will be infinite. It will go up to some term into x to the power n, where n is like it becomes an infinite series. Okay, so anyway, so now when we apply the approximation here, so suppose I have 1 plus x to the power n, and n is very small compared to, sorry, x is very small compared to 1. Okay. So for example, x could be something like 0.04, like we've seen. Then in the series, 1 plus x to the power n is equal to 1 plus nx plus nn minus 1 by 2 x square plus, these terms, x square, x cube, x to the power 4, etc. are all negligible. Okay, so that means they are tending to 0, because x is very small compared to 1. So here, for example, you can see that x square will be 0.0016. Okay, x cube will be 0.000064. Okay. So these are all tending, they are negligible. Yes, Nishchay?
Sir, if n is at the range of 50, then 50 or a power of 100,000, then we cannot ignore this x square, right?
No, see, the thing is, it's not about n, it's about the value of x. No? You're understanding the point? If x is small compared to 1, no? Then this coefficient is so small that it doesn't matter if you're multiplying something over here, which is large, but this will be so small that this will be negligible compared to this nx term. No?
Yes, sir.
So even if n is large, like let's say n is 10 to the power 3, but x is small enough, then this third term will be negligible compared to the second term at least.
Yes, sir.
So we can still, so what we can do then is we can neglect the higher terms. Okay. So therefore in this expression, the higher terms, that is the terms of x square, x cube and onwards, can be neglected. Okay, compared to nx, compared to this term. So that's how we say that, okay, this series becomes approximately equal to 1 plus nx, provided of course x is very small compared to 1. So this is the proof, you can say, or this is the logic. More than proof, it is the logic of the binomial approximation. Okay, so once again, like I have discussed this point before with you, but I'd just like to reiterate that since I'm giving you the PDF of the lecture notes now, so you don't have to make very detailed lecture notes during the class, okay, because then your attention is on making the notes rather than the learning part. So what you do is in the class, at least the numerical problems that I'm doing, or if I'm asking you to try out any numerical problems, those you do step by step on pen and paper. But rest of the things, you don't need to write everything in that much detail. You can just jot down some rough notes, and later you can use my notes, or you can make your own fair notes from my notes for your reference. Okay, so that way we can proceed also more smoothly in the class. Plus your concentration should be on learning each of the points and asking the doubts and things like that if anything is not clear. So I'm sure all of you are doing this anyway, but still I'm just reiterating the point.
Sir, there above that 1 plus x to the power half, sir, you have written it goes on till x to the power n.
Sir,
Sir,
and
how
n,
it will?
because see, what will happen here, na, that in your power series, you can see the value of this n you should not confuse with this one. Okay, this value is half. Okay, and this is like n tending to infinity. You're getting my point now?
Okay, sir.
So
Sir,
this
means
series
that
will be
is
like
1 plus x to the power
1
infinity.
plus half x plus some coefficient to x square plus some coefficient into x cube plus some coefficient into x to the power 4, and like this series goes on and on. Whereas when this is a whole number, okay, or a natural number, then the series stops when x's power reaches that natural number.
Okay, sir.
Got it? So anyway, our concern right now is not even with the higher terms. Now our concern is just with the first term. So you can understand the coefficient of the first term is always the power. Now, so here the power was 4, so it's 1 plus 4x. Here the power was half, so it's 1 plus half x. So in general, for 1 plus x to the power n, okay, sometimes in my handwriting x and n might look similar, so try to avoid that. So the first term will be nx, okay, and the higher terms are getting neglected because x is small compared to 1. So x square, x cube, x to the power 4, and so on, whatever the higher terms are, they are getting neglected. So that's how this works. Okay. So now let's see how we can prove our formula of the derivative of x to the power n using this. So coming back to differentiation, and by definition, or what is called in maths, it is called by first principle. Okay, so the first principle, differentiation by first principle, is this definition that derivative of the function fx is given by this limit formula. This one is called differentiation by first principle. If we solve this limit, so let's come back to this. For differentiation of x to the power n, you can see that differentiation of x to the power n, when we apply the first principle, will be limit delta x tending to 0, x plus delta x to the power n minus x to the power n upon delta x. Okay. So if I directly put delta x as 0, I'll get 0 by 0. So that's not solvable. So I have to do some manipulation. Now I can't directly apply binomial theorem because this is not 1 plus something. So I will do that manipulation here, that I'll take x common from the first bracket. So what I'll do is from this bracket, I'll take x common. So I can write that like this now, that it is x to the power n into 1 plus delta x by x to the power n minus x to the power n divided by delta x, which I can further now write as x to the power n. I can take common here and write this as 1 plus delta x by x, this thing to the power n minus 1, okay, divided by delta x. Okay, so up to this step, I hope is clear to all of you, right? Okay, now see comes the critical step. This term, is where we can apply the binomial approximation. 1 plus delta x by x to the power n. Think of it like a 1 plus y to the power n, where y is equal to delta x by x. So obviously y is very small compared to 1 because delta x is tending to 0. Okay, so this can be approximated. So this can be approximated as 1 plus ny. So that is 1 plus n times delta x by x. So this term can be approximated as this. Okay, so substituting this term as this over here. Okay, so we'll substitute this here. So next step, this will become okay, and there you are. Next step, you can see that the job is done. Now again, remember delta x is not equal to 0, it is tending to 0. So we can always cancel this delta x and this delta x, and we have the formula that this is n into x to the power n minus 1.
Sir, can you repeat this? I did not get the step.
Which step? This one?
Sir, 1 plus from that 1 plus delta x by x to the power n.
So see, 1 plus delta x by x to the power n ko na, we'll solve it separately. So I've taken it here. Okay. Now I can write this 1 plus delta x by x as 1 plus some other quantity y to the power n, where y is what? Y is delta x by x. Right?
Yes, sir.
Okay. So this expression becomes what? 1 plus y to the power n, where y is what? It is very small compared to 1, because look at this fraction delta x by x. In this, delta x is tending to 0, no? And x is some general value of x.
Yes, sir.
So even if suppose x is something very small like 0.001, but even then your delta x is tending to like, you know, like 10 to the power minus 500 or 10 to the power minus 50,000 or whatever you can imagine. So that delta x by x will always be very small compared to 1. So y is very small compared to 1. Okay. So this is the binomial approximation for this step, that 1 plus y to the power n is approximated as what? 1 plus ny. Okay. This step is clear now?
Yes, sir.
And then just resubstitute y as what? Delta x by x. So 1 plus y to the power n is 1 plus ny, gives you this. So now substitute this back in this expression. So this whole bracket inside 1 plus delta x by x to the power n, this is replaced with what? This is replaced with this. This is replaced by this when I substitute this. So this bracket, the power n bracket becomes 1 plus ny where y is n times delta x by x. Okay, and then this one and this one cancels out. So it's just algebraic manipulation, right? You can see this.
Yes, sir.
So if you revise this later once, you will see it's not too different to how we had done for the proof of x cube or x square. But there we just opened it directly by using binomial theorem. And here we are first taking that x to the power n common. And instead of expanding this whole thing by binomial theorem, we are just using the first term of the binomial theorem because we are using the approximation. So 1 plus delta x by x to the power n, instead of expanding it fully by the theorem, we are just applying the approximation, that this third, fourth, and all those terms are negligible. So that's how that's happening. Right. So hope this proof is clear. Okay. Now, having done the proof, as I told you, the proof is not going to be important for us. What is going to be important is the application, which you've already seen in those questions that we've done before. Okay.
Sir,
So, yes.
Sir, can you show the notes? I'm noting that.
Yes, yes.
Right. Sir, finally we get x to the power n into n by x, right?
Finally, we get x to the power into n by x, right?
So then we
so that
wrote
x
it as,
cancels in the denominator. No?
yes, sir.
We're getting this, right? So now this thing, no? That next step that becomes this.
So n into x to the power n minus 1.
Yes, n into x to the power n divided by x step karenge. So we'll get this step next finally. So this becomes the formula for us, that differentiation of x to the first principle, or by the definition method, by the limit method, that is coming to this. Okay. So this is hence proved by the first principle method. Okay. Or method of limit. Right, so this is clear now, right?
Yes, sir.
Yes, sir.
Okay. Now we will come to some more formulas. So apart from this, of course, you have seen the application of these properties. That differentiation of a constant multiplied by a function is equal to the constant multiplied by derivative of the function. We can write it like this now. And the differentiation of the sum or difference of two functions becomes derivative of first function plus derivative of second function. Okay, and this applies to minus also. Okay, and we have seen that differentiation of a constant is 0. So these are some of the properties. Now we will see the next set of formulae of differentiation. Okay, so more formulae. So first of all, we'll see the differentiation of all trigonometric functions. Okay. The basic trigonometric functions. So differentiation of sin x.
Cos x.
Very good.
Cos
Like cos x.
Cos
Correct. Differentiation of cos x is
Minus
sin x.
Sin x.
very good. That's minus sin x. Okay. Then differentiation of tan x.
Sec
Sec
square
square
X.
x.
Sec square
sec
x.
x.
Sorry, how much is it?
Sec square x.
Sec square x. Yes. Okay, and differentiation of cot x.
Minus cosec square x.
Minus cosec
Very
square.
good. Minus cosec square x. Okay. Differentiation of cosec x.
Minus cosec x cot x.
Very good. Minus cosec x cot x. And differentiation of sec x.
Sec x tan x.
Tan x.
Sec x into tan x, or tan x into sec x. Okay. So now again, at a later stage, okay, when you learn little bit more trigonometric equations and all, you can always prove these. Okay. The proof of all these can be done by first principle, but I am not going to get into the proof of these at this stage. Okay. If any of you are curious and you want to try out the proofs, you can do that, and I can always help you out. And so you can get in touch with me and show me the method you're using. You can just send it to me as a message or a click of it, and I'll help you out with that. But for us, what is important that you should remember these formulae. These 6 formulae are very critical, and out of these 6 also the first 3 are the most critical: sine, cos, and tan's derivative. Okay. Then next we have exponential function. So before we get into the derivative of exponential function, let us learn a little bit more about the exponential function. So what is the value of this exponential number in this? What kind of number is
constant, no?
Yeah, E is a constant, but you know what
The
is the value?
2.71.
Irrational number.
2.71.
Irrational number. Right? Its approximate value is 2.71. E's approximate value is 2.71, but E is actually, it is an irrational number like pi. So it means it's a non-recurring, non-terminating decimal. Now, what is the very interesting, very interesting property of this function? So this exponential function has a very important property, that the derivative of the function or the differentiation of the function is the function's value itself. Okay. So what this means is that the slope of the tangent at any point x equal to x is equal to, that slope is equal to e raised power x, but also the y coordinate is also e raised power x. So whatever is the value of the y coordinate, that is equal to the slope of the tangent. So for example, the graph is such that x equal to 0, the y coordinate is 1. Okay, the slope of tangent is also 1. Okay, at x equal to 1, the y coordinate is e, but the slope of the tangent is also e. Okay, at x equal to -1, for example, the y coordinate is e raised power -1, that is 1 by e. So we can approximate that as 0.32 or something like that. Okay, so the slope of tangent, sorry, this will be about 0.34. So slope of the tangent m will also be 1 by e, or approximately 0.34. Okay, so next we'll just understand in terms of graph what this means. Okay. But first of all, you can write down this basic formula, that for the exponential function, the value of the derivative is this. It is a unique function which has, in mathematics, which has this property that at every point on the function's graph, the value of the y coordinate is equal to the slope of the tangent. Okay, so the value of the y coordinate equals the slope of tangent. So that is the interesting property that this function has.
Sir, could you please explain that last point again, that while y coordinate
So see, the formula of the derivative, okay, is that differentiation of e raised power x is equal to e raised power x. Okay. So now given the function y is equal to e raised power x, what is dy by dx? That's also e raised power x. Okay. So if I select any value of x, like x equal to 0, what is the y coordinate at that point? It's e raised power 0 or 1. Okay. But what is the slope of the tangent at that point? That will also be 1. If I take the value x equal to 1, what is the value of the y coordinate? It's e raised power 1, or approximately 2.71. But what is the slope of the tangent? That's also e to the power 1, or approximately 2.71. Understood this pointer now?
Yes, sir. Now got it.
So that is the very interesting and unique property that the exponential function has. That at any point on the function, the value of the function itself, the value of y for that given value of x, equals to the slope of the tangent. Okay, so let's understand what this property means in terms of graph of the function. What it means in terms of the graph of the function is that if you look at the approximately drawn graph of y is equal to e raised power x, that will be a shape or a curve that looks something like this. Goes on rising very rapidly from here. So you can see that as x tends to, so this is the graph of y is equal to e raised power x. You can see that, for example, at x equal to -1, the value of y is 1 by e. At x equal to 0, the value of y is 1. At x equal to 1, the value of y is e. At x equal to 2, the value of y is e square, and so on and so forth. Okay. Now the interesting thing about this is if we draw the tangent at various points, you can see that the slope of the tangent is such that that is also increasing as x goes from -infinity towards y. So if I draw the tangent here, it has a slope that's comparatively less compared to the tangent drawn at this point. The slope is more. At this point, the slope is even more. At this point, the slope is even more. Okay. So if you zoom out of this graph, okay, you see that the shape of the graph is such that as the graph rises rapidly like this, at every point along the x-axis, if you're going along the positive x-axis, the slope of the tangent is increasing, as is the y-coordinate. But not only that, it's increasing in such a way that at any point, the slope of the tangent, let's say at x equal to x1, the value of y is e raised power x1. Okay. But the slope of this particular tangent, this tangent at x equal to x1 will have a slope which is equal to e raised power x1. So that is the property of the graph. Okay, that so also you can see that for this function, limit x tending to minus infinity is 0. Okay, and also the slope at x tending to minus infinity is 0. Okay, because you can see that this line, it becomes almost flat as x tends to minus infinity. And limit x tending to infinity, the value of e raised power x tends to infinity. You can see because this rises very rapidly. So the slope of the graph also, as x tends to infinity, tends to infinity. That means this becomes almost like a vertical line. Like you have the graph of tan x at x tending to pi by 2. Like that, it almost becomes a vertical line. So the slope tends to infinity. So same thing over here happens for the exponential graph as x tends to infinity. So that is about the exponential function and its derivative.
Excuse me, sir.
Yes, beta.
Sir, the last part you said the slope tends to infinity. I didn't understand that.
Okay, so let's try to figure that out. Okay, what it means by saying that the slope tends to infinity. Okay. Now, if you have a vertical line like this line would be x. X is equal to something. It would be, let's say, x is equal to 2. Okay. Now, what is the slope of this line? It's tan 90 degrees, no? So it is undefined.
Yes, sir.
Okay, but suppose I have something like this where I have another line where it's almost 90 degrees. Okay, so this theta is equal to 90 minus some delta theta, where delta theta is tending to 0. So what will be tan theta? It will be tending to infinity.
Okay, sir. Yes, sir.
Understood the point? No? Because the tan graph, it looks like this, no? If you look at the values of tan theta with respect to theta, so as theta approaches pi by 2, from the left hand side, the value of tan theta approaches infinity. But then, of course, the moment theta becomes greater than pi by 2, it approaches minus infinity and it comes back to this. And then again, 3 pi by 2. Thing like this happens. So you can see first quadrant tan is positive, second quadrant tan is negative, third quadrant tan is again positive, fourth quadrant again it is negative, like this. Okay. So now imagine this line slope in the graph, or rather this curve's slope. So now you look at this exponential function, it's going like this. Okay, now suppose I've taken a very large value of x, like x equal to 50. So according to my formula, what should be the slope of the tangent at this point? The slope of the tangent m should be e raised power 50. That itself is a very large number, you can see. It's almost like 3 to the power 50. Okay. But compare this with somewhere where, let's say, x is equal to 200 now. So you can see that the slope has increased so much now at that point.
Yes, sir.
So now as x is becoming larger and larger, like it's becoming like 10,000, 1 million, and it's tending to infinity. So this curve will almost tend to become like this. It will tend to become almost vertical. Okay, like this line is tending to have theta equal to 90. Like this curve will tend to become vertical. So the slope of the tangent will tend to become infinity. Okay, beta. So this point is clear?
Yes, sir.
Okay. Whereas on the other hand, when you go on the negative side, the further you're going away from the from the origin on the negative side, the more and more flat your line is becoming. So as you're going to x tending to minus infinity, is becoming almost perfectly flat. So the slope is tending to 0. So that is the other aspect of the exponential graph.
But sir, if the slope is becoming rising so rapidly, why does
Yes.
it take so long for it to tend? Why does it have to tend to? Why doesn't it definitely just become a vertical
Because see, the
line?
thing is, can we say e to the power 50,000 is infinity? We can't say, no? It's a finite number. It's very large, but it's finite only, no?
But sir, on the graph, if you've said that it rose so vertically, I get numerically it's not infinity, but still.
Yeah, so see, that is the difference between practice and theory, no? Like if we actually sit down and jot a graph, if we write a computer program to actually, make all these dots for various values, we will see that it will go outside the screen very soon because it rises so rapidly. But theoretically, for it to go to infinity, this x also has to tend to infinity. You understanding the point, no? Because infinity is such a
Yes.
large number that we can't imagine it, no? So when we say e raised power x is equal to y, for y to become that sort of a large number that we can't imagine it, that is infinity, x also has to go to infinity. So down the x-axis, you have to go to such a faraway point that it's actually gone out of scale. You can't actually plot it. So that's when this will also go out of scale.
Okay, sir.
Understood the point? Okay.
Yes, sir.
So yes, that concept is a bit abstract. Okay, infinity itself in that sense is an abstract concept. Okay. Next thing we will look at, so we've looked at the formula of differentiation of the exponential function. Now next formula we will look at is the logarithmic function or the natural log function. So we should understand that the natural log function is what we call the inverse function of exponential function. ln x is the inverse function. So what this means is that it is inverse of exponential function. It means that if y is equal to ln of x, it means that x is equal to e raised power y. So it's an inverse operation. Or if x is equal to, or if y is equal to e raised power x, it means that x is equal to ln y. That is the meaning of that. It's an inverse function. So as you know, this is log to the base e of x. Now this one has a property that differentiation of this function is given by what? You people know this?
1 by
1 over x.
1 by
1 by x.
So here as x increases, the derivative actually decreases. So this has the reverse property. Okay, this has the property that, so therefore, for the function ln x, okay, the slope of tangent 1 by x, this is such that as x tends to infinity, the slope tends to 0. And as x tends to minus infinity, the slope tends to infinity. So we'll see that the graph of this function has that particular property now. Okay. So just make a note of this formula compared to the graph of the function.
Sir, can you repeat what an inverse function means?
Inverse function means it's the reverse operation. So for example, y is equal to x square is inverse function of square root. So that means that if you look at these two functions, y is equal to square root of x and y is equal to x square, they are inverse of each other. So what that means is that y is equal to x square implies that x is equal to root y, or y is equal to root x implies that x is equal to y square. Okay. So like that, if y is equal to ln of x, that means that x is equal to what? E raised power y. Understood the point? No?
Yes, sir.
So for example, for this function, if we take x as e, then y becomes how much? It becomes 1. So now let's look at the reverse of this. So it means that x is equal to e raised power y. So if I take y as 1, x is equal to what? E. Yes, Nishchay, you have a doubt, Beta?
Sir, here you have wrote as x tends to minus infinity, slope tends to infinity. How is this possible? 1 by minus infinity will tend to 0.
I'll demonstrate that how that is possible. Oh, sorry, it's not minus infinity as it tends to 0.
Yes.
As it tends to 0. Okay, so please make a correction here. This was not minus infinity. This is supposed to be 0. So it's clear now, Nishchay?
Yes.
Okay. Okay, so let's understand this in terms of the graph of the exponential function.
So just a second, I didn't take down the note for the exponential function. Can you just
Okay.
scroll up once?
Okay, I'll scroll up just a minute. Achha, exponential function or logarithmic function?
No, so exponential.
Okay.
The note for it that you had written.
Achha. Okay, so the explanation of this was clear, na? That as x tends to infinity, how the slope also becomes infinite.
Yes, sir.
Okay. Okay, so if you look at the graph of the natural log function, so first of all, we should understand that the log function or natural log function is only defined for x being greater than equal to 0. Okay, ln 0 is not defined. Okay, and ln of any negative quantity is again cannot be defined. So the graph looks something like this. It's like this. Ln of 1 is equal to 0. Ln of, for example, 1 by e is equal to minus 1. Ln of 1 by e square is equal to minus 2. Ln of 1 by e to the power, let's say 1000, will become minus of 1000. Okay. So ln of x as x tends to 0. Okay, it tends to minus infinity. Now, when we look at the slope of the graph at various points, you can see that the slope is decreasing now. Okay, so much so that by the time x tends to infinity, this is supposed to become almost a flat line. Okay. So at
Sir,
any point, yes.
sir, 1 by 0, it will be minus infinity or infinity?
So the interesting thing is that x tends, no, it's not the slope. Now I'm talking about ln x. Okay, so that's why I've shown you this, that like x tending to 0, you can think of it like this now, ln of 1 upon e to the power some number where that n is tending to infinity.
Yes, sir.
Okay, so that will tend to how much? It will tend to minus of n. So that's minus infinity.
Yes, sir.
So that's right. Now when we talk about the slope, yes, the slope will tend to infinity. So you can see that, so for this function, the slope at any point is 1 by x. Okay, so at any point x like this, if I draw the tangent, that tangent has a slope equal to 1 by x. So you can see that at this point, the slope will be equal to 1. At this point, the slope will be equal to e. At this point, the slope will be equal to e square. At this point, the slope will be very large. It will be e to the power 1000. So therefore, at x tending to 0, what happens to the slope? The slope tends to infinity. It becomes almost a vertical line. Whereas as you go on the positive side, you can also see that ln of e is equal to 1. Ln of e square is equal to 2. Ln of e to the power 5 is equal to 5. Ln of e to the power 1000 is 1000. But what about the slope? The slope is decreasing. So the slope at this point is becoming how much? 1. The slope at this point becoming how much? 1 by e square. Sorry, this is 1 by e. Okay. The slope at this point becoming 1 by e to the power 5. So the slope at this point, which is very large on the x-axis, right, somewhere here, let's say, e to the power 1000. Okay. So the slope of the graph at this point is becoming very small because the graph is becoming almost a flat line. So the slope is 1 by e to the power 1000. Okay. So now when I take ln of x, x tending to infinity, that itself is infinity. It tends to infinity. But the slope at x tending to infinity will tend to 0. So as you're going from x tending to 0 to x tending to infinity, your graph is rapidly rising from minus infinity towards plus infinity, whereas the slope of the graph is declining. It is almost vertical at 0, so it's infinity tending to infinity, and then it's decreasing, 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 and the slope tends to 0 because this curve almost flattens as x tends to infinity. Okay, so that is the shape of the exponential graph and the relation of the slope of the tangent or instantaneous rate of change with respect to its shape. Abhinav, to answer your question, ln is the short form for log to the base e. Okay, so ln x is basically the short form for logarithmic function, but to the base e, where e is the exponential number. Whereas when we use the term log x without any base, it is the short form for the standard log to the base 10. So the standard logarithm is, if we say standard log of x, it's to the base 10. But if we say natural log of x, it's to the base e.
Yes, sir.
Okay, so that's the terminology. And ln is the short form for natural log.
So what is their significance?
Of the ln function?
Yes, sir.
The significance is that it is the inverse of exponential function. Exponential function significance you've understood, no? It's a function whose derivative is equal to the value itself. It's a unique function in the world which has that property. And the inverse of the exponential function is what? It is a logarithmic function. So if I say a is equal to e to the power b, it means that b is equal to natural log of a. So that is the significance of the ln. Just like anti-log is the inverse of log, no? When we talk about base 10. So like that.
Okay, sir.
So these two are very important in terms of application of calculus in physics. Later you will see that there are certain types of systems which have properties that can only be described by exponential or its inverse, which is a logarithmic function. So once again, if you're comparing the exponential and logarithmic function, that also gives a very interesting result. Okay, because they are inverse of each other, the comparison of logarithmic function and exponential function will look something like this. So in the same graph, if I draw two functions, okay, but before I draw the two functions, I will also have to draw a guideline to help me. And that guideline will be the line y is equal to x. So if this is approximately the line y is equal to x, then the exponential function will look something like this. Okay. Whereas the logarithmic function or the natural log function will look something like this. Like this, where this point is 1, 0. This point is 0, 1. And for this one, at any point x, the slope of the tangent is 1 by x. Whereas for this one, at any point x, the slope of the tangent is equal to y itself. So in general, we can also say that if we have some point here where x is equal to a and y is equal to b, so b is equal to ln of a, then the corresponding point here will be like this. Just drawing it with a different color, where this point will be b comma a. So you can see they are a reflection of each other with respect to this line y equal to x. And they are like a mirror image of each other, these 2 points, AB and BA, because this now implies that A is equal to e to the power b. So they're inverse of each other. So that is a comparison of these two graphs. So this is just like some additional general knowledge for you, okay, how these graphs look, etc. When we applied them to actual physics problems, you will see that these properties and these little features of the graph that we're discussing and the rate of change and all that, they will become significant in understanding those things. Okay. Okay, so now coming back to differentiation and properties. Yes, Nishchay, you have a
Oh,
question?
just 1 second.
Yeah, Sam. Yeah, Nishchay, you have a question, beta?
Yes, sir. Sir, what is the significance of E and tensor? Why do we take only their log? I mean, why do we take log to their bases only? Why not other
No,
numbers?
it's not that we take only to them. Like we can take log to any base. For example, we can express, log of 8 to the base 2 is 3. Right? You know this,
Yes.
Or, log of, let's say, 60 to the base 4 is 3. Okay, that's perfectly fine. We can do that. But the standard values that we take, one is that when we go with the decimal system of numbers, we take log to the base 10. And the other is when we go with the natural log, we make use of the exponential number. So why this exponential number is significant? Because the exponential property has that unique feature. The exponential function has this unique feature that derivative is equal to the y coordinate. So that is what makes this actually significant. The value of E becomes significant because of that. You understanding my point, beta?
Yes, sir.
If we look at the graph of any function of this type, that y is equal to a raised power x, where a is some positive number greater than 1, the shape of the graph will be more or less like this. The shape of the graph will be like this only. But depending on the value of a, it might be like this, or it might be decreasing more rapidly here and increasing more rapidly on that side, or decreasing less rapidly and increasing less rapidly. That all depends on the value of a. So if you take a as, for example, 1.2, or you take a as 2, or you take a as 5, you can compare all these graphs. But none of them will have the feature that the slope of the tangent is equal to the y coordinate. That will only happen when a's value is equal to e. It has this particular feature. So that is why that particular graph out of this family of functions is very important. Out of this family of a to the power x, where a could be any positive number greater than 1, this one is a very significant one. And the inverse of this function is which one? Is the natural log function. Okay, so it is the inverse of exponential function. And that is why that one is significant. So that's why these are the two significant bases that we take for the log function. The E for the natural log, or the base 10 for the decimal system. Decimal system, again, it has its own importance in mathematics. That's why. Whereas exponential number has its significance because of this rate of change property. Okay. So hope that clarifies the point, Beta.
Yes.
Okay, now coming back to differentiation and some important properties. So more properties of differentiation. Now, for example, in your worksheet, I have given you some questions where it appears to be like there's a product of two functions, like y is equal to, let's say, x to the power 1/3 into x plus x square. Suppose I want to differentiate this. Okay, but here we can actually differentiate this by simplifying this. We don't need to use any additional property. We can just say, or suppose this is 2x. We can just say that y is equal to x to the power 1/3 into 2x plus x to the power 1/3 into x square. So we can just make it 2x to the power 4/3, correct, plus x to the power 7/3. Okay, and then we can differentiate this. That's fine. When we differentiate this function, we can just use the distributive property and take the constant outside. So we don't need any additional property compared to what we have learned. We can just use this only, the direct formula now. So the derivative of this function will quite easily come out to be like this. 2 into 4 by 3 x to the power 1 by 3, right? Plus 7 by 3 x to the power 4 by 3. So this will become 8 by 3 x to the power 1 by 3 plus 7 by 3 x to the power 4 by 3. Whatever. We can take some term common and all that also. So this is fine. But what if we have a function of this type now, where it is expressed as the product of two separate type of functions like sine x into 1 plus x square? Now it's not going to be of much use. Even if I open this bracket, the first term is easy, it's sine x. But what about the second term? It is sine x into x square. So I don't have a formula for directly differentiating sine x into x square. I definitely cannot take sine x outside because it's not a constant. So we need a separate property for these type of functions, where we are multiplying two different type of functions. One is
Transcendental.
it's a transcendental function. This is an example of a transcendental function because it has the trigonometric expression as well as the algebraic expression. Okay. So for that purpose, we have an additional property of differentiation, okay, which is the product rule. So the proper way of writing the product rule is that if y is such a thing that it is a product of two functions. So let us say it is fx into gx, where fx and gx are individual functions. Okay. Example, y is equal to x square into sine x. Okay. So you can see that fx is equal to x square and gx I would express as sine x. I can write in reverse order also, it doesn't matter, but y would become equal to fx into gx, this kind of thing. Okay. Then we have the property that the differentiation of y with respect to x, which is the derivative of fx into gx, is given by this principle, that it is one function into derivative of other plus other function into derivative of first. Okay. So again, this is where that shorthand notation comes in useful, because otherwise writing it with the
Sir,
d
your
by
voice
dx becomes more lengthy.
breaking.
Okay. So here we understand that g prime x is just a short form for differentiation of gx, and f prime x is just a shorthand notation for differentiation of fx. And it's precisely for these kind of lengthy expressions that we use the prime notation. So this is called the product rule. We can also write this product rule in ultra short form. We can write it like this, that y is equal to f into g, where f is fx, g is gx. So differentiation of y with respect to x will become fg prime plus gf prime, or we can also write it as gf prime plus fg prime, it doesn't matter, where f prime is differentiation of fx and g prime is differentiation of gx. So it's all about notation, how shorthand we want to make it. So this is like the ultra shorthand notation, the same thing. Okay. So you can finish writing this down and then just try out this question yourself. Y is equal to x square sine x. So find dy by dx. Okay. And the slope of the tangent at, let's say, x equal to pi by 4. Find the value of dy by dx or the slope of the tangent at x equal to pi by 4. So remember, when we talk about transcendental functions in particular, it becomes even more important that the value of any angle should be expressed in the SI unit, which is radian, and not in degrees. So even if the question had asked that find the value of the slope at x equal to 30 degrees or 45 degrees, you should convert it to radian and then only substitute in the value of the slope. Okay, so this is very important. So just try out this question, people, after noting this down.
Excuse me, sir.
Okay, very good. I'm getting the correct answers. Dhruv, Abhinav, Nishchay, Mansi, and all your answers are correct. So let's just apply this systematically over here. Okay. As you get used to all these properties and formula and all, you can do a lot of direct calculation work also. But in the beginning, you should just be careful. So I'll just do this as a comparison. So f into g, where I understand f is x square and g is sin x. Okay. So f prime should be derivative of x square. So that is 2x. Okay. And g prime should be the derivative of sin x, which by the formula we've learned today, I know is cos x. Okay. So the differentiation of y with respect to x, if I'm writing it properly, I should write it like this, that it's first function into derivative of second function plus second function into derivative of first function. And I can reverse this order also, it doesn't really matter. Okay. So next step, you can see it is x square into cos x plus sin x into 2x. So x square cos x plus 2x sin x. Okay. Or if you're just doing it by a quick method of comparison, you can see that dy by dx is fg prime plus gf prime. So just substitute from here. So it is x square cos x plus 2x sin x. So like eventually you will get to a stage where you can just look at this function and directly see that, okay, its derivative will be first function, that is x square into differentiation of second, plus second function, that is sin x into differentiation of first. So that's it. So you can just do this step, single step, and it will be enough. But again, like if you're new to differentiation, which I'm sure many of you are, okay, then at least in the beginning when you're working out the everyday class worksheets and all, okay, go with a systematic method, write down all the steps as if it's a board exam and you're going to get marks for each step. And eventually you will see, you'll get enough confidence and practice that you can, at the MCQ exam level, you can just write it in one step without making a mistake. So it's very important, that you start with accuracy and don't worry about speed. Okay, speed will come with practice. But if you're, too much in a hurry in the beginning, when you're not yet enough practiced, then you will get into the habit of making careless mistakes. And then you have to go from, from inaccuracy and speed to accuracy. So that is a much more difficult process. If you're very, very slow, even if it takes you 1 hour to solve something which should technically not take more than 20 minutes, but your accuracy is 100%. It is just a matter of few weeks every topic to practice enough that your speed will come. But if you get mistakes into your system, it becomes part of your method of problem solving, that you're always in such a hurry that you are prone to making careless mistakes, then it's going to take months of work to remove those kind of mistakes. Okay, so do not be in a hurry at all. Okay. Yes, we always say speed is very important in JEE exam, it's very important, but that's when you come to the end product, when you have practiced enough and revised enough, at that stage the speed is the most important thing. But at least in the beginning, speed is of no importance at all. What is important is, first of all, proper understanding of the concepts, then step by step application of the concepts, and then as you're applying the concepts, you should be very precise in your pen work, so there's no chance for making any mistakes. The more you do that, the more you will see you can progress faster and faster, topic by topic, without any difficulties. Okay. So typically in things like differentiation, which are basically like, mechanical process, it's just application of algebra. So it takes a lot of patience to do complicated questions. And often the difference between, being successful and not being successful is having that patience to do the steps meticulously without making a mistake. Don't be in a hurry. Do less number of questions if required. take breaks in between if required. There's no need to do 3 hours continuously of worksheets. Do 1 hour, take 10-minute break, then again do 1 hour. It's fine. But don't allow careless mistakes to come into your system. Okay, from the beginning, if you keep note of this, it will save you a lot of troubles at a later stage. Okay. All right, now let's come to the next property. If a function is expressed as the quotient of two functions, this type. So for example, if I have a function of this type, then how I differentiate it? So it's again given by a formula. Now this one is a little bit more complicated. It is denominator into differentiation of numerator minus numerator into differentiation of denominator divided by the denominator whole square. So this is a bit of a monster formula, and it takes some use to getting familiar with it. Okay. The example that I like to keep in mind to remember this formula, when I was a student, I used to always get confused with, what is the subtraction in the numerator, whether it is fg prime minus gf prime or it is gf prime minus this. So I just remember the example of tan x, which I'll now express as sin x by cos x. Okay. Now I know from formula that the differentiation should be sec square x, but let's also express it as, okay, this cos x into differentiation of sin x, okay, minus sin x into differentiation of cos x divided by cos square x. So that is how you can prove that tan x's differentiation is sec square x, provided you already know that the differentiation of sin and cos are what they are. Okay. And you know the identity that sin square x plus cos square x is unity for any value of x. And of course, you know that 1 upon cos x is sec x. Okay. So this is a very easy way to just quickly verify this formula. And in case you're confused between what is subtracted from what, you can just check. If you made a mistake in the application of the formula and you take the denominator in place of the numerator, then what will happen is you will get some other answer. You'll get minus 1 by cos square x, or you might get something even funnier. Okay. So you can quickly verify what we have done is correct or wrong. This is the quotient rule. Or the division rule. So let's try out this question next. You can also write this in an ultra shorthand notation that the function is some numerator divided by some denominator, where numerator is some function fx, denominator is some function gx. So the derivative of the function becomes denominator into differential of numerator minus numerator into differential of denominator divided by square of the denominator. Oh yes, Abhinav, I forgot about the value of the slope of the tangent in the previous question. I'll just go back to it and verify your answer.
Yes.
So I wanted the slope of the tangent at pi by 4, no? So this thing we'll
Yes.
see. Yeah. So now I want the value at x equal to pi by 4. So that will become pi by 4 square cos pi by 4 plus 2 times pi by 4 times sine pi by 4. Okay. Now we can use an approximation that pi square is nearly equal to 10 and pi is 3.14. So this will become nearly 10 by 16, okay, into 1 by root 2 plus pi by 2. So that is 3.14 by
It
2.
is pi radians, no?
Huh. Yeah, I mean pi is always radians. Okay. And radian is a dimensionless number, as you know, because it's arc upon radius, so it's dimensionless. So it's basically just a number. Just like sine of pi by 4 is also a dimensionless quantity, does not have a unit, because it's a ratio of two lengths. So, and also 1 by root 2, we can always approximate like this, that it's root 2 by 1, root 2 by 2. So next we can approximate root 2 as 1.4. It's approximately 0.7. So, it's like this, 10 by 16 into 0.7 plus 3.14 by 2 into 0.7. And then you can simplify this further. So I'm not putting more time into this. So this will give you a numerical value of this if you want.
Yes.
So could we just leave it in terms of pi, because that's what
You can leave it like this also. It's fine. You can leave the answer like this, that, or you can just write it as 1 by root 2 into pi square by 16, correct, plus pi by 2. This is also fine.
So can we convert pi into degrees and cents, or
No, that is the thing, beta. You have to understand that degree is not the SI unit now.
yes?
So if you want the numerical answer for this, you will have to put the numerical value of pi, which is approximately 3.14. Right, no? So if you want to know the slope of the tangent, no, it's a particular value, no, it's a number. So how we'll get that number? We'll get it by substituting pi in this as 3.14.
Yes.
So whatever this ugly fraction, when I solve it now, whatever number it gives me, that number is the actual slope of the tangent. It is the value of tan theta for the tangent which I draw at x equal to pi by 4 for the graph of that function. Okay. Let's come back to this question now. So for this function, we will take dy by dx as denominator into differential of numerator minus numerator into differential of denominator, which you know is e raised power x, divided by the denominator square. This will become e raised power x into 2x minus x square plus 1 into e raised power x divided by e raised power 2x. So we can simplify this a little further. So we get e raised power minus x into 2x minus x square minus 1. Now later we'll see there's another method of doing this particular question. We could have also expressed it as e raised power minus x into x square plus 1 and then just applied product rule. But when we apply product rule to differentiate e raised power minus x, we'll have to apply something called chain rule. That is why I avoided this method and we just went with the quotient rule method. Yes, so Vedant, Abhinav, Aryan, Dhruv, all of you got this correct. Nishchay.
So, but this y is equal to e to the power minus x, sir, we can do it without using chain rule also, right?
कैसे बताओ? अच्छा, 1 by e raised power x square. You can do that. If you are differentiating, you know, that's like, it'll be a bit of an ugly method. So you can also differentiate it this way, that it is denominator into differential of numerator, which will be 0 because the numerator is a constant, okay, minus numerator into differential of denominator, so that's e raised power x only, divided by denominator square, so that will be e raised power 2x. So you can see that this will become 0 minus e raised power x upon e raised power 2x, so that is minus of e raised power minus x. Okay, so this is a bit of a lengthy method, but yes, we can do it this way also. And then we can put it in the product rule, and you know, so two-step process we can do the differentiation. But if we are using the quotient rule anyway, then we can just use it for the whole function only. No?
Sir, here e raised to power minus x into x square plus 1. Sir, we can directly use product rule also.
But usme we have to differentiate e raised power minus x. No? So there's no direct formula for that. No? Differentiation of e raised power x is e raised power x, but differentiation of e raised power minus x, how we know that it is minus of e raised power minus x? That actually comes from chain rule, or we can in this case also show it from the quotient rule.
So e raised to power minus, sir, if there would have been only e raised to power x, then we could have
फिर तो
done
कर
it.
देते हैं, फिर directly product rule से करते हैं, फिर तो there's no problem only, right?
Yes, got it.
Okay. Okay, so this is about the product rule and the quotient rule. Okay. Now next we'll talk about, so we'll just look at an introduction at this last thing today. Okay, we'll look at something called composite functions. Okay, so composite function is basically a function of a function. So you can think of the term composite function as a function of a function. So in general, we'll express it as y is a function of another function of x. So for example, if we have y is equal to square root of x square plus 1. So we can think that, okay, gx is equal to x square plus 1. So then y is what? Y is square root of gx. Okay. So the function f is nothing but the square root function. So on x, we are first operating g to get x square plus 1. And on g, we are now operating f, okay, to get square root of x square plus 1. And that is equal to our y. So to get from x to y, we have to do two steps. First, we have to calculate x square plus 1 from x. And then we have to take square root of that. So whenever that kind of thing, there's a function inside a function. So there's the square root function outside, and inside that there is x square plus 1. So in that case, we call it composite function because it's a function of a function. And the general way of writing a function, composite function, is it is f of gx, or we can write as g of fx. We can use any symbol. The symbol doesn't matter, but as long as we understand that it's a function operated on another function. So another example of this would be if we have y is equal to sine square x. So we can see here what we've done is on x, we have first operated the sine function. Okay, so that means our gx is equal to sine x. And then on that we have operated f of gx. So that is a whole square function. So that is sine square x. So f of gx is g square x. So that's why it is sine square x, because f is the whole square function. So first of all, how do we recognize a composite function? This is how we recognize a composite function. It's a function inside a function. So this is whole square of sine x. Okay, so it's a function inside a function. There's the square function, whole square function, and inside it there's the sine function. Or we can have something very transcendental, like we have y is equal to ln of sine square x. So this is a function inside a function inside a function. From x, we have first operated sine x. Then we have operated the whole square function. So we have come to sine square x. And then on that, we have operated the ln function. So we've got, so it's a 3-step composite function. So that's a slightly more complex type of composite function. Okay, so now differentiation of composite functions is done by something called chain rule. So I'll just take you through the basics of chain rule today. And our next lecture, we will concentrate on a lot of examples of application of chain rule. So what we do in the chain rule is, if the function is expressed in this manner, it's a composite function. In the chain rule, the first step is substitution. That is, we introduce a dummy variable. Okay, so let us say z is our dummy variable and we have written that as g of x. So z is our dummy variable. So once we do that, then we can say that, okay, y is nothing but f of z. So in terms of z, y is a simple function. It is not a composite function anymore. So step 1, we introduce the dummy variable, or we do substitution. Then the next step is the critical step, which is the chain rule step. So in the chain rule step, we express the rate of change of y with respect to x as the rate of change of y with respect to z multiplied by the change or rate of change of z with respect to x. Okay, and the final step is the re-substitution. So in the chain rule only, we substitute this over here. And z was gx. So next step, this becomes derivative of this function multiplied with derivative of this function. Okay, and finally that becomes f prime of gx into g prime of x. So that becomes our final answer. So this entire process has to be done very systematically for any function which is a composite function. Okay, so let's just look at the application with one example and very systematically we'll look at. So we'll take that rather simple case of y is equal to sine square x. So we can see that on x we have operated the sine function. So we've got sine x. Okay. And then we've operated the whole square function. So we've got sine square x. Okay. So this is our g and this is our f of g. Okay. So what we'll do is step one. So I want to find the instantaneous rate of change. Okay, so first step, remember, was the substitution step. So I have to introduce a dummy variable. So here, this thing should be the dummy variable. This should be z. Okay. So we will say z is equal to sine x. So the moment I say z is equal to sine x, my y becomes very simple. It is z square. So next step is the chain rule step. Okay, that the rate of change of y with respect to x is logically the rate of change of y with respect to z, because now y depends on z, multiplied by the rate of change of z with respect to x. Okay. This is almost like a logical step. Like for example, if you know that your car runs so many kilometers per liter and a liter costs so many rupees, so then you want to find out that how many rupees per kilometer. So you have to just establish a a unitary method chain like this, that per liter how many kilometers and per liter how many rupees. So from that you can calculate per kilometer how many rupees. Okay, like that. So this step is a logical step like this. So now let's substitute. So in place of z we will in place of y we will substitute z square. Okay, and in place of z we will substitute sine x. So this will become 2z into sine x. And the final step, re-substitution. So in re-substitution, we will replace z as sine x. That's what we have done earlier.
Sir, that will be cos x.
Yes, sir.
Oh,
Z
sorry,
into
that will be
cos
cos x. Yes, my mistake. Yes, correct. Thanks for pointing out that. So differentiation of sine x with respect to x, that should become cos x. Okay. So finally, dy by dx, which is 2z cos x, will become 2 times sine x cos x. Okay. And if we like, we can use the formula that 2 sine x cos x is sine 2x also. But at this stage, I'll just leave it as 2 sine x cos x. Okay. So now I know that this is the rate of change. So for example, for y equal to sine square x graph, I want to find slope of tangent at x equal to something, let's say pi by 6. So I know that slope of tangent at pi by 6 will become 2 times sine pi by 6 cos pi by 6, which by formula I can also write as sine pi by 3. Okay. Or I can directly substitute. It is 2 into half into root 3 by 2. So it's root 3 by 2, which is basically sine. So this is a simple example of the method of application of chain rule. Okay. So we will look at more complex examples of application of chain rule in the next lecture, and we'll develop enough practice that we can skip some of these steps in between. But at the moment, like any question you are doing by chain rule, I would like you to, as I said, be very systematic in applying the steps. Yes, so Aryan and Mansi, your answers were correct. Very good. Okay.
Sir, I had a doubt in in chapter exercise.
Sorry, beta, what was that?
Sir, I had a doubt in chapter exercise of module which you asked us to read, page 26, as I wrote in chat box.
Yeah, so just send it to me on the this thing now on the WhatsApp. I will send you a hint for that doubt. Okay, beta.
Okay, sir.
Okay.
Sir, I have also sent you a few doubts on WhatsApp.
Okay, I'll take a look at them when I get some free time today, or maybe early tomorrow, and I'll send you the hints for it. Okay.
Thank you.
So that's okay. And we'll also have some doubt session for physics this time on Sunday. So if any of the doubts are not cleared after the messages and all, we'll take care of that in the doubt session. Okay. So that's it for today's session, people. Wish you all the best. Thanks for attending. Hope you've understood everything.
Bye, sir.
Okay.
Bye,
Thank you,
sir.
sir.
Thank
Bye,
you,
sir.
sir. Bye, sir.
Thank you, sir.
All the best.
Bye, sir. Thank you, sir.